the admiral, when you had a meeting and he would say, like, the meeting starts at 8:30, he would lock the door to his office. And if you were there at 8:30 and 5 seconds, you missed the meeting, and then there was hell to pay while you didn't go to the meeting. So he has maybe control issues. And then when I taught this class in Brazil, they said, well, your classes start at 8:30. And I was like, I'm there in the room at 8:30 and there's nobody there. And then finally about 8:45, people start kind of wandering in the room. And then maybe at 9 o'clock, you actually have enough people to start talking. So it's quite a different culture. Yeah, it's basically half an hour. Anyway, the admiral also, when he arrived, he said, I do not like surprises, even on my birthday. And so anyway. Dude.
On that point, tomorrow, please, everybody be here at 8:30 because we cannot be late tomorrow. It's critical. We have 20 of these. We have 21 and a 20-meter piece. It's 7 hours. You don't have extra. There's no. We don't. I'll bet who goes first. Yeah, you want to do it on? We'll draw randomly.
Are we going to have suspenseful random draw?
Unless you want to self-edit it by themes, people talking about similar things, writing and close to each other, and build up upon that.
Okay, you guys get together then and just make out a list of who goes in which order, and we'll take it however you guys want it. Okay, well anyway, here's my project for about the last 10 years. So we'll see what I've been up to, at least part of what I've been up to. So we've been talking mostly about doing remote sensing of optically deep open ocean waters where what you're interested in is retrieving chlorophyll or KD or particulate concentrations or backscatter, something like that. So what I'm going to talk about today is the other half of remote sensing, which is shallow waters, optically shallow waters. And optically shallow simply means that bottom reflectance is a significant part of the water leaving radiance. And there you may still be interested in retrieving IOPs, but what you're usually interested in is retrieving bottom depth and bottom type. So who cares about shallow waters? Well, first of all, the military, because they want to do amphibious landings when we invade Canada or whoever's next on the list. And it's not like we can just call up Iran and say, we're planning to invade you, can we come in and make some good bathymetry maps so we know where to land? So I actually got into this business when the Naval Research Lab asked me to look into how well we could do what I'm going to show you today. And of course, I guaranteed them that it could not be done, but I would still take their money to prove that to them. It turns out it actually works quite well. So the military is interested in having maps that show the bathymetry, that is how deep the water is and what's on the bottom. They're mostly interested in, is it soft mud, hard coral, rocks, or whatever. They're not particularly interested in whether it's this species or that species of coral. They just don't want to run up on the coral. On the other hand, there are other people like ecosystem managers who want to have maps of bottom depth and bottom type because they're interested in managing coral reefs, seagrass beds, kelp forests, and all those sorts of things with the goal of managing fisheries and recreation. And they're interested both in episodic events, like I have my seagrass bed here on the coast of Florida. I know what it's like today. Now a hurricane comes through and completely redoes things. So what happened because of the hurricane? Or maybe there's a harmful algal bloom, or there's a pollution spill, something like that. And then they're interested in long-term changes. In coastal waters, you have land usage changes, so fertilizer runs off of farms, puts nutrients in the water. That causes phytoplankton to grow, which causes the water to become less clear, which then doesn't give enough light to the seagrass beds and corals and so on. But all of these people need maps at a scale of preferably 1 meter but at most 10-meter resolution. They want to actually be able to get, see there's a coral here and there's not one over here. And so they can't use kilometer scale like you get from a satellite. They often want you to go out and get this imagery and have the map on the person's desk the next day. So that could either be for military use the next day, or it could be that there's a harmful algal bloom going on, or there's a pollution event. And they might want you to be able to just repeat that on demand. Wow, this is great. Fly again right now and give me another picture 4 hours later, rather than waiting 3 days for the next satellite overpass and then having it be cloudy anyway. So is NASA concerned with this? Yeah, they are. There was a big program that's just been funded called Coral Reef Airborne Laboratory. It's a $30 million chunk of money managed by Eric Hochberg. And the whole idea here is that coral reefs, of course, are very important. They're traditional food sources for a lot of people, especially in the tropical Pacific waters. So those coral reefs are going downhill, some of them quite quickly, from global climate change and local land uses and local fishing, overfishing and so forth. There's issues of shoreline protection, recreation, and so on. And then there's a plot here you can't see, but it's basically, here's atmospheric CO2, low CO2, high CO2 gives you, changes the carbonate concentration in the water. And then here's, let's see, yeah, it's called deviation from the day's temperature. But basically, the idea is if we have low CO2, low acidity in the water, we're in an area where the shallow waters, reefs, are dominated by corals. And as carbon dioxide goes up and the temperature goes up, we're moving into a region where the reefs will not be dominated by corals, because the corals can't handle the high acidity, high temperature water. So we're seeing this kind of change already going from what we have now up to this non-coral reef, sort of reef ecosystem. Here's a typical coral reef, and you can very quickly go from having a lot of corals to having almost no corals, but all kinds of yucky things growing on the bottom that are not pleasing to scuba divers and not suitable for hiding the little fish that live in the corals and so on. So that's why NASA is funding this. And once again, we want meter scale imagery. Well, how do you get that? You can send divers in the water and have them throw down little random transects and count the species of coral and all of that, but that's extremely laborious and expensive. You can tow things in the water that either have a video camera on the bottom or some other kind of sensor, and yeah, that gives you transects back and forth, but you'll notice that boat drivers don't like to take their boats over coral reefs where the water's only a meter or so deep. And so that's, once again, very limited coverage. And in a big area like Hawaii here, you may have just a few spots where you have a field program, and even in the area of the field program, you may only have a few stations here and there. So the only way to really study this is getting very high resolution imagery from either a satellite, if possible, or from an airplane. And so in this corals study, what they're interested in is how does the health of the coral reef depend on all the things like water temperature, water acidity, clarity of the water, and so on. And so they've been funded to do a study of all these spots shown in green here and make high resolution airborne hyperspectral bathymetry of these areas, along with concurrent field measurements of all the water chemistry and optics and so forth, and try to come up with a better understanding of how coral health is related to the physical and optical environment. So yeah, NASA has a big interest in this. And now, a couple of words on how are we going to make these imagery measurements. Well, we want meter scale and we want hyperspectral. So fine, let's just buy a hyperspectral imager and put it on the satellite next to MODIS, and we'll get our imagery. Well, you do a little back of the envelope calculation. The MODIS sensor, it's going around the world roughly 45,000 kilometers in an orbit. It takes 99 minutes to go around the Earth. So that means it's going about 7,500 meters per second. And you can go online today, give them your credit card number, and you can buy a compact airborne spectroradiometric imager, CASI. It's a commercial hyperspectral imager made by a Canadian company, and it gets 33 pictures per second. Well, if you do the arithmetic, 7,500 meters per second, it takes me 0.03 of a second to grab one image, and meanwhile I'm doing that, the satellite has moved about 225 meters. So that has blurred out my 1 meter pixel, stretched it out 225 meters. Well, that's not going to give me a very good looking picture. So what I really need is to have an exposure time of maybe a 10,000th of a second, in which case my satellite has only moved a meter. So I could get a meter scale image, but the problem is I don't have a hyperspectral imager that can have a 10,000th of a second exposure time. So I really cannot get hyperspectral meter scale imagery from a polar orbiting satellite. You just can't do it, both for technical reasons and there's just not enough photons. So I got off on this question about, how many photons do you actually get at a satellite from a meter of ocean surface, so photons from water leaving radiance. And there's a webbook page where I actually go look at all the little solid angles and this and that and plug in the numbers. And the answer is there's almost no photons of water leaving radiance getting to from a 1 meter square patch of ocean getting up to a satellite, because the solid angle for a meter square on the ocean from 700 kilometers up is so small, et cetera, there's just not enough photons there. Well, what do you do then? You can either view a larger piece of the surface area, so that gives you more photons, and of course that's what an imager like MODIS or VIIRS is doing. They're looking at a square kilometer, for example, and then you have 1,000,000 times more photons than you do from 1 meter. And they look at, or you could also look at the surface for a longer time. So you sit in a geostationary orbit looking at your 1 meter. Well, then you can expose your, take a 5-minute exposure if you want to, but of course your solid angle is much smaller because you're much higher, so that's sort of undoes the advantage of having a longer exposure time. We want hyperspectral, so we want to take the photons that are there and break them up into, say, 5 nanometer bandwidths. Well, if I take larger bandwidths, I can basically bin all those photons together, but then I've lost my hyperspectral signal. And of course, the imagers that do get high resolution, like Landsat, for example, they don't give you a hyperspectral signal. They're giving you much broader bandwidths. And I can buy a bigger telescope so I collect more photons at the top of the atmosphere, but then that makes the sensor extremely expensive. Or I can some way have multiple sensors looking at the same spot, add all the numbers together, but then that makes everything more expensive, and so on. So you look at all these things and you come to the conclusion that really the only thing you can do to get enough photons from a square meter is to get close to the ocean surface, so you have a bigger solid angle, and fly really slowly so you can have longer exposure times. And that means you're going to get an airplane, you're going to put your hyperspectral sensor on the airplane, and you're going to fly as low and slow as you can. And slow sometimes means like 100 kilometers an hour, so very slow. But you can then get enough photons to have an acceptable signal to noise ratio, and so on down the line. So that's what people have done. So the science issues that I want to talk about today are two things. How do you do atmospheric correction for airborne hyperspectral stuff, and what kind of retrieval algorithms you use. Now, we're in a place where we're interested in the bottom reflectance, and that means the black pixel assumption that Jeremy talked about often fails because you have bottom reflectance making those near IR wavelengths non-zero. So the black pixel doesn't work You also are usually working in coastal waters and off the coast of, the US or China or Arabian Peninsula, wherever. And those areas often have absorbing aerosols, which mess up your atmospheric correction. So those things we have to talk about. And then if you remember from my lecture on statistical algorithms, I showed an example of a band ratio algorithm that worked pretty well in very shallow waters, like down to 3 or 4 or 5 meters. But then when I applied it to an image that had depths down to 10 meters, it gave me good answers for the shallow part of the image and totally wrong for the deep part. And that's because the band ratio was non-unique for, you can have 2 different water depths, 2 different remote sensing reflected spectra, but they'll have the same band ratio. So a band ratio algorithm is often, they often have non-uniqueness problems. And of course also in coastal waters you have often really complex mixtures of phytoplankton and minerals and dissolved substances and pollutants and so on. So it's hard to come up with a statistical algorithm that even if it works well in one water body, it's not going to work over there, or it works well in shallow waters, but not if slightly deeper waters. So we're going to have to figure out some other way to do the retrievals and how to get around non-uniqueness. Okay, so 3 techniques for doing atmospheric correction. The black pixel that Werdell discussed last week works quite well for open ocean waters, which are often case 1. And it was really designed for multispectral satellite ocean color remote sensing back all the way to the days of CZCS. And so anyway, we've already seen that, but I've already commented that this often doesn't work in shallow waters. So there's 2 techniques that I'll outline here, one called an empirical line fit and one called radiative transfer techniques. So as we'll see in a moment, the idea with the empirical line fit is we're going to make some measurements of remote sensing reflectance at the sea surface while our sensor's flying over, and we're just going to get a correlation between what I measure at the sea surface and what the sensor measured, and we'll use that correlation to correct the at-sensor radiances, and I'll show you how that works. And the other idea is if I know the atmospheric properties, so aerosol type, relative humidity, water vapor content, all those things, then I can simply run an atmospheric radiative transfer model and compute the path radiance, including surface reflectance, between the surface and my imager. So I'll just compute that, and then I know the right number to subtract out of what I measured up here in order to get water leaving radiance. And I'll show you how that works. Okay. So back to this black pixel business, here's just some hydrolyte runs where I put in case 1 water, chlorophyll of 0.05, so that's typical kind of number you get in these really clear coral reef areas like the Bahamas or tropical Pacific. So here's remote sensing reflectance as a function of wavelength, and okay, up here in the visible where we're actually interested, numbers are like 0.02. We go down to where we're going to use 2 wavelengths to do our black pixel atmospheric correction, and I think Jeremy was talking about using 748 and 865. So anyway, at those 2 wavelengths or something similar, we're down 3 orders of magnitude from the values at the visible. Well, that's good enough to say, this is 0 water leaving radiance. But now if I come along and I put a sand bottom at say 1 meter, that's the orange line, well, I'm still not seeing the bottom out at 865, but now I am starting to see the bottom back at 750, and that's 1.5 orders of magnitude greater. And if I put that sand bottom at 1 meter, that's the red line, now my water leaving radiance because of bottom reflectance is just as big at the near IR as it is in the visible. So using a black pixel assumption's totally out the door. Same thing if I put a lot of minerals in the water for case 2 water, the purple and the blue curves, those highly scattering minerals can raise the bottom reflectance up to being, a couple of orders of magnitude more than it would be in case 1 water. So, okay, black pixel doesn't work. So what we really need is some kind of atmospheric correction technique that does not require 0 water leaving radiance in the near IR, so we don't have to deal with the black pixel thing. It needs to work for any water body, case 1 or case 2, and even these very clear low chlorophyll waters are often case 2 because they have extra CDOM in them. And the CDOM may not be coming from land runoff or from phytoplankton, but it's coming from benthic organisms. So corals and seagrasses put out a lot of CDOM into the water. So it may be very clear water, but it can also be highly absorbing in the blue because of CDOM, but the CDOM's coming from what's on the bottom, not from phytoplankton. And then we need to have some technique that works for any atmospheric type, including absorbing aerosols. And we need some kind of technique that does not require me to be in the field making measurements like I need for, I'll say, the atmospheric measurements so I can run a radiative transfer model. Well, those are my requirements. And you know, there's this saying, faster, cheaper, better, pick any 2. Well, here it's pick any 3. This is the great unsolved problem of remote sensing here. And I can, you know, come up with a technique that doesn't require black pixel, works for any water body, works for any atmosphere. Oh, but I have to have the field measurements to do it. Or I can come up with a technique that doesn't require any field measurements, but then, you know, it may require a black pixel assumption and so on. So nobody has solved this problem yet, and that's a good project for you guys to work on. But, yeah, Emmanuel.
There's also another method that people use, and that's if you somewhere in your scene, you have a place where you can apply black pixel. Say it's a reef near deep water, like in the bottom, then assuming the atmosphere is not changed over your scene, use the deep water.
Yeah.
Things like that. So
You can do that. Once again, though, I could go back here and say, does not require a deep water pixel, because most of my imagery, I don't have any spot in the image where it's optically deep water. So we kind of rule out that possibility for most imagery. And sometimes you can do it, but in general you can't. Okay, so a couple of words about this empirical line fit business. So the way that works is while the sensor's flying over, you get out there in your small boat and you run around and you make remote sensing reflectance measurements at various places in the image. And then you're going to take those measured spectra and you're going to correlate them with the image spectra from the sensor when it's looking at the same spot where you were making the measurements. And you just come up with a little correlation function which is called the empirical line fit, and then you're going to use that to correct all the other pixels in the image. Okay, so here's an example. Here's an image of a place called St. Joseph's Bay in Florida. This is land right here. Shallow waters ranging from several meters deep in these channels here up to emergent seagrass beds that are dry at low tide. Okay, so here's an image from a sensor called WorldView 2. It's multispectral, but it does give you meter scale imagery, although the signal to noise ratio is pretty low, but it's usable. So at these spots here where there's a little cross, people ran around in a small boat and they measured the remote sensing reflectance at the time the image was taken, or at least that's the idea. And it doesn't matter whether you're in deep or shallow water or, you know, what's on the bottom. You just want to get a remote sensing reflectance spectrum. And you're making that, you know, as a function of wavelength. Okay, so here now, if we look at the 546 nanometer band, and we look at the remote sensing reflectances measured at these different points here at 546 nanometers, and then our top of the atmosphere measurement from the WorldView 2 sensor is actually in digital counts. So I simply plotted what I measured on the ground versus what I measured on the satellite, fit a line to it, which is the empirical line fit, and now I'm going to take this curve and use it to correct every image in the pixel. I'm assuming that the atmosphere is the same over the whole image. All right, so what I do, let's say I have a, well, okay, so right here, here's the top of the atmosphere signal, the orange curve, and digital counts. And so I'm at 546 here. So let's say I want to atmospherically correct this top of the atmosphere value. Well, I look over, where is it here? And that says that's like 170 digital counts. So I come up here and I say 170 digital counts. Come up, that's maybe a little less than 0.006 per steradian on remote sensing reflectance. So the 170 becomes the little less than 0.006, and I've used this curve here to simply turn my digital counts at the top of the atmosphere into a remote sensing reflectance at the surface. And then I have a different function for every wavelength. So I can take my top of the atmosphere measurement, turn it into a sea level remote sensing reflectance spectrum, and then I plug that into whatever algorithm I want to use to retrieve bottom depth and so forth. So that's the simple idea of how an empirical line fit works. But you notice the problem is we have to have somebody out there making the measurements at the time of the overflight. I can't make the measurements a week beforehand because the water properties in the atmosphere are different from a week later when I did the overflight. Well, that all works fine on a science experiment when you can set everything up ahead of time. You have the people in a small boat. Those people are usually known as graduate students. And so you send them out there, they get all the measurements, and life is good. But in general, you really can't use this except in sort of pre-planned experiments because you don't have the ability to go out in the field and make the measurements. And of course, if there's variable aerosols or something over the area of the image, then even if the correction is good on one side of the image, it may be bad on the other side. So there's a lot of problems there. And another one is if the satellite's looking at you down at this angle where you're making the measurement, and you build the empirical line fit here, but then at this part of the image, you have a different atmospheric path length. So even if you do a good job looking in this direction, you may not do a good job looking at a different direction because of the difference in the viewing geometry. The sun geometry gives you different path length and so forth. So it can work, but it's got its problems. The other technique, and this is what's used mostly by the US Navy, which flies all kinds of hyperspectral imagers around, are radiative transfer techniques. And here the idea is that if I know the atmospheric conditions, I can just run a radiative transfer model and compute for this exact condition. Sun's up here, I'm over there, I'm looking at this direction, here's the atmosphere, here's how much path radiance and surface reflectance I have, so I know the number to subtract out. Well, they've developed a big correction code called TOFCA. It originally started out as being called ATRM, atmospheric removal. That was developed by people at the University of Colorado, and then they sort of gave it out or something, and the Navy started using it and saying, we're using ATRM to do our atmospheric corrections. But then the university people said, oh, well, we don't want you to call what you're doing ATRM because ATRM is really our thing. So the Navy renamed ATRM as the algorithm formerly known as ATRM or TOFCA. So the software is officially known as TOFCA now. But it's all the same software down inside. So what the Navy did was they said, we don't want to run the computer program every time. We want to build a big lookup table. So they took a whole range of atmospheric conditions, aerosols, water vapor, all of those things. They took a whole different range of sun angles, a whole different range of viewing directions relative to the sun, a whole range of elevations of the sensor. So maybe I'm flying at 1,000 meters 2,000, 3,000, whatever, up to 30,000 meters. So they took all of those different combinations of what they might encounter in the real world, and that turned out to be 60 million different combinations of viewing directions and atmospheric conditions. And for each one of those, and different elevations, for each one of those, they ran this really fancy radiative transfer code and computed the number they need to use to correct a pixel looking in this direction for this atmosphere when I'm at this elevation and so forth. So they built a big lookup table, 60 million values to start, and that took them several months of time on a 256 processor silicon graphics supercomputer that they had. But now they have the big table. Okay, so then you can come along, you have got your image, you know where the sun was, you know where you're looking, you say, I know what the atmospheric conditions were, and then that tells you where to go, and I know how high my airplane is, so that tells me what number to get in the lookup table to do my atmospheric correction. Well, that's great, and it has a real advantage in that you can do a different atmospheric correction for every pixel in the image. So with one airplane, you have different viewing directions, different path lengths, and so forth, and in principle, each one of those should get a different atmospheric correction, which you can do with TOFCA. With the ELF, you're going to do the same atmospheric correction over the whole scene, which may or may not be good. But of course, this has the same problem as the ELF. You have to know the atmospheric conditions, which means, you know, put a guy out here and let him send up a weather balloon and have a sun photometer and all of that and get all the atmospheric corrections you need. So TOFCA is only as good as how good you guess the atmospheric corrections. If you guess good, you get a good retrieval. If you don't guess the correct atmosphere, you get a bad retrieval. And so when you look at imagery, here's TOFCA corrected imagery here. So this is land, this is a bay here, and then there was an airplane flying back and forth this way, taking these strips of imagery. And as soon as you look at this, you know it's not a good atmospheric correction because you can see the edges of the flight lines here. Now, really, the atmosphere and the ocean are not coming in stripes like that. You should just see a continuous gradation. So you kind of know something's not perfect about my atmospheric correction. And in this case, you know, the middle of this band is looking straight down. The edges of the band are I'm looking off this way and looking off this way by maybe 30 or 40 degrees. So something's not quite right about the atmospheric correction. And if you take this kind of image and you process it, as we'll see in a minute, to get something like bottom depth, well, here's another big bay area. And so what we're seeing on the retrieval is it's bottom depth. Red is 1 to 2 meters, or 0 to 1 meter, and on down to the deepest blue here is 4 to 5 meters. Well, the general retrieval is pretty good. You know, here it's next to shore, it's shallow, and then it's deeper, and then it's still deeper. So in general, this is a correct retrieval. But you can also very clearly see the flight lines in the retrieval because the atmospheric correction wasn't really as good as it should have been. So this might be usable for you, it might not be, but in any case, you can see here the individual flight lines, but you see them also in the retrieval, and that's because of bad atmospheric correction. Emmanuel.
There's another variation of ELF that people can use today, and that's if you have an object on land of no reflectancy environment. So often you see example torrents of material of no reflectance that they spread fly over and go over, possibly several times that day.
Yeah. Yeah, and yeah.
I was going to say, down in Puerto Rico, we've actually used that method. And we've tried different atmospheric corrections down there. We've found that kind of a variation on the ELF method using called the cloud shadow scheme, actually developed by Lee. We found that actually works the best
Yeah.
down there. We've compared it with the Tofka results. In the Tofka, we usually don't get very good results.
Yeah.
But the ELF method usually produces, or some sort of variation of it usually produces pretty good results.
Yeah. Yeah, there's lots of ways, and like Emmanuel said, if you have an object of known reflectance, then you can sort of tweak Tofka, for example, till you get that answer, and then use those atmospheric correction or atmospheric values. And let's see here, I guess. Okay, so here's an example of a bad atmospheric correction. So here's from an image where I get the image from the Navy. They say, process this, do your work on it. First thing I do is just plot up a bunch of spectra. So I went in, I pulled out a bunch of spectra, and notice they all level out here at about 0.003 per steradian, all the way out to 800. Well, that's not physical. Those spectra they might not be zero, but they shouldn't just level out like that. So I'm immediately knowing that they've undercorrected the imagery. That is, they didn't subtract out enough atmospheric radiance to some way bring this down to somewhere down in here. It just looks phony. Well, when I do a retrieval on this, and we have acoustic bathymetry in blue across a transect of the image, and I do my retrievals, I do sort of okay back here in the shallow waters, 2 or 3 or 4 meters deep. But then, as the water gets deeper, as I go offshore, my retrieval levels out at about 3 to 5 meters. Well, what this is telling me is that there's no way I can have spectra this bright in the near IR unless I have a bottom that's no more than 4 meters or so deep that would give me reflectance out here in the near IR. So this is consistent with these spectra. So then I send the image back to the Navy and I say, look guys, you need to tweak this a little bit and use some different atmospheric conditions or whatever you want to do, but give me another image. So then they send me back an image where these guys are now down here. The whole spectra are just pulled down a bit. Well, then I do my retrievals on that. I get the green curve, which is an extremely good fit to the acoustic bathymetry all the way down to 14 or 15 meters. So bottom line, bad atmospheric correction, bad retrieval. Good atmospheric correction, good retrieval. Very simple. All right, there's a recent paper by Victoria Hill and company where they did a combined Tofka ELF thing. So what they did was they went out, they measured their remote sensing reflectance spectra at various points in the image at the time the image was acquired, and then instead of building an EOF out of those, or an ELF out of those, what they did is they took each spectrum they measured and they looked through the Tofka database to find the closest fit Tofka generated spectrum. And so they did that for all of their points. And now each of those closest fit Tofka generated spectra had some set of atmospheric properties that went with it. So they averaged all of those together and got kind of an average set of atmospheric properties that would reasonably well reproduce the RRSs that they measured. And then they took those atmospheric properties to search through the Tofka database and do then a Tofka correction for all the rest of the pixels in the image. And that worked pretty well for their image. So they were happy. And you know, there's ways you can do things like that that will improve on one or the other. And you know, I'll just leave it at that. That's kind of the state of the art. And lots of people are trying lots of different things here to see what works the best in general. Okay, so enough on atmospheric corrections. Now let's talk about retrieval algorithms. And I've already said that these statistical band ratio algorithms don't work because of non-uniqueness. And so therefore, what people have developed are various kinds of spectrum matching algorithms. And we'll talk about 2 flavors of those. The semi-analytical model, where you're going to match your measured image spectrum to some kind of semi-analytical model and in forcing that match, you will determine the unknown parameters of the model, which are things like the bottom depth and the bottom reflectance and the water IOPs, or you can pre-compute a big database of remote sensing reflectances, and for each of those spectra, you know what the bottom depth was, the bottom reflectance, etc. And then you'll match your image spectra to the database spectra and find out the closest match, and that then becomes your retrieval. So we'll see how each of these works. Okay, so Zhongping Li had a couple of classic papers on this semi-analytical approach. So just to outline what he does is he says, okay, here's our old friend, backscatter over absorption plus backscatter, and the remote sensing reflectance in deep water is basically proportional to BB over A plus BB and some proportionality constant. And at that point, you've got single scattering theory, but he lets the proportionality constant also be a function of BB over A plus BB. So that kind of adds in effects of multiple scattering. So he starts out with a little formula like this for deep water, and then he adds in corrections for shallow water. So what he does is he takes his deep water term, and then there's a 1 minus and this function of KD and KU. So the light has to go down with KD attenuation, gets reflected off the bottom, and comes back up with some KU attenuation. And so there's an e to the minus k times the depth is h. So notice if h goes to infinity, k's are positive, this term goes to 0, and you just get back the deep water part. And then he adds on a term for the bottom reflectance. Same sort of thing, the light goes down, hits the bottom, gets reflected by whatever the bottom reflectance is, so that's some number between 0 and 1, and then there's an additional term added in here for the bottom reflectance. And once again, if h goes to infinity, then this term goes to 0. So he writes all this stuff out, and he finally comes up with a formula that says remote sensing reflectance is his deep water term corrected by a term for the bottom, and then corrected for a term for the bottom reflectance here. And now he's got all these unknown parameters, G0, 1, 2, D0, D1, A0, A1, etc. So those are all unknowns. Now what he does is he says, okay, let's model, here's absorption and backscatter are in there. Alpha is the sum of absorption plus backscatter. So he's going to model his absorption and his backscatter just like you guys have seen numerous times, where absorption is pure water, which we know, a phytoplankton term, a CDOM term. Then he's going to model the phytoplankton by some little function where he assumes that he has these wavelength dependent coefficients, and then he parameterizes it in terms of the phytoplankton absorption at 440. Same sort of thing. Here's a CDOM spectrum. He parameterizes that in terms of the CDOM absorption at 440, which he doesn't know, but then an exponential for the wavelength. Backscatter is water plus some function for particles, and so on and so on. So you can go read the paper and see what he did there. He assumes a Petzold phase function. So he basically models all these things. And then what he does, well, we end up now with, based on these kinds of equations, phytoplankton is modeled in terms of A phi at 440, CDOM is modeled in terms of absorption at 440, and so on. So he now ends up with this set of equations where the unknowns are the absorption by CDOM and phytos, the backscatter fraction, the bottom reflectance, and the bottom depth. So those are all in this big semi-analytical model. And things like the sun zenith angle. Now, what he does is a zillion hydrolite runs, where he puts in different solar zenith angles, different chlorophylls, different yellow matter concentrations, different bottom reflectances, all of that kind of stuff. He generates this big database of hydrolite generated remote sensing reflectances, and then he does this big nonlinear curve fitting, basically, where he says, force my model to fit all of these hydrolite generated spectra and give me the best fit set of model parameters here. So he's now determined actual values for all of those little parameters that are in his model. And what's left over are the U, so that's absorbing and backscatter, the bottom depth, and the bottom reflectance. So now he's got his semi-analytical model. Now we're going to take that out in the real world and say, here's my image, here's a remote sensing reflectance spectrum, force this equation to fit that spectrum, and by so doing that, your free parameters are now the U, the H, and the rho, which contain the things he wants. So he's going to do then another nonlinear fit for each pixel of his image and come up with the best fit, bottom depth, bottom reflectance, and water IOPs. So that's what the Lee algorithm does. It's widely used. There's this HICO sensor that recently died. It was on the space station. It's a hyperspectral imager. And for the HICO, they use Tofka to do the atmospheric correction and the Lee algorithm to then do the retrievals of bottom depth and bottom type. So basically what you're going to do is you'll make an initial guess for the CDOM, phyto, etc. values, these 5 numbers. You make a guess. You use those in the semi-analytic model to predict remote sensing reflectance. You compare that prediction with the measured remote sensing reflectance that you're getting from your imager, and it's after atmospheric correction. And then those won't agree, so you have some rational way of tweaking all these parameters to get a new guess at the parameters, and you just keep cycling around here until you finally don't get much change in these parameters, and then you say, okay, the current values here are my solution for this pixel. And I think he uses the Levenberg-Marquardt thing here, I'm not sure, but basically it's just a big nonlinear curve fit. And then you finally hopefully get a solution. Now, sometimes this just goes off into la-la land and you don't converge, but okay, that's life when you're doing nonlinear inversions. The nice thing about it is there's no in situ measurements required here. He doesn't have to go out in the field and make some kind of measurement like you do with ELF or Tofka. That's all been done in a sense when you did the hydrolite runs. Okay, so that's how his technique works, and how well, or that's how it works, and how well does it work? Well, here's application to some real imagery. Here's his measured A-phi at 440 versus retrieved. And it's not too bad. If you take these values and stick them into his little spectral shapes for A-phi at 440, here's a couple of different places. This is chlorophyll of 0.15, chlorophyll of 2.3, but in both cases, the black lines are the measured spectrum and the open lines are the retrieved. I think that says, yeah, it says determined, so retrieved. Darn good agreement there between what was measured in the field versus what was retrieved from the imagery. So that's pretty encouraging. Here's his retrieval of CDOM 440, once again pretty good. And here's his retrieval of bottom depth all the way down to 25 meters. That's a very good retrieval to be able to just take an airborne hyperspectral image and come up with a bottom depth. If it says it's 15 meters, well, maybe it's really 14 or 16, but you're still pretty close. So it works very well, and it's widely used. Okay. The other kind of spectrum matching technique was what I and a bunch of other people, there's about 8 people on that paper, what we developed. And the idea here, well, what Zhongping Li does is he did all this work beforehand of fixing up this semi-analytic model and doing all these hydrolite runs and so forth. This technique, we do all this work beforehand of creating a big database, and then we use the database for the retrievals. So what we're going to do is we're going to create a database of remote sensing reflectance spectra that will correspond to any combination of water IOPs, bottom depth, and bottom reflectance that I'm going to see in my imagery. Okay, so who's downloading there? Anyway, I probably now have some toxic virus here that's going to wipe out the rest of my talk. Okay, so what the requirement is that in this database, there's going to be a spectrum that will correspond to any spectrum I'll see in my image. That's the underlying idea. And so to create this database, I basically just put a big do loop inside Ecolite. And then what I did was, if I want to process an image from the Bahamas, for example, I had some measured data from AC9s on Bahamas waters so I could kind of see the range of IOPs. So I just generated a bunch of absorption spectra, and notice these are very CDOM-like spectra because there's a lot of CDOM in the water down there because of the benthic stuff. They have extensive seagrass and corals there. So anyway, all the AC9 data I've ever seen from this Bahamas area, taken by people like Emmanuel Boss in the back row there, they're all somewhere in here. So I've got a wide range that's wider than what I've observed, and there's absorption coefficients, scattering, some backscattering coefficients. So I'm going to take all these combinations of IOPs. I have a bunch of measured bottom reflectance spectra, and these are from sands, seagrass, corals, macrophytes, whatever was out there, sponges, you name it. So I've got all these bottom reflectance spectra, and then I'm going to put the bottom at 1 centimeter, 25, 50, 75, 1 meter, and then by 25 centimeter steps down to 15 meters, and half a meter steps down to 20, and then I threw in 25, 30, 50, and infinitely deep. So I now have this big combination where I had 25 sets of IOPs, I had 123 bottoms, I had 83 depths. Multiply all that together, it's about 250,000 different combinations of water IOP, bottom depth, and bottom reflectance. And each one of those I'm going to run through Hydrolite and compute the associated remote sensing reflectance. So that took about a week of time on my laptop here. But now I have this big database that should be representative of anything I'm going to see in the Bahamas. Need another database for the Gulf of Maine, but that's okay. So here's just 1% of those spectra, and they're anything from very dark spectra down here, which would be maybe 15 meters of water with a seagrass bottom, and very bright spectra up here, which could be bright sand in 25 centimeters of water. So anything imaginable in there.
What's that one line where it's like almost vertical and yellow?
Oh, out here? That's probably a red edge, or it is a red edge, and it's probably something like seagrass in 1 centimeter of water. So you're seeing that really, and you know, these guys are doing the same here. It's just that that's the most extreme one. But you're now seeing that chlorophyll red edge that starts out just past 700, and there's only, you know, 1 centimeter or 25 centimeters of water, so there's not enough water there to knock that back down. But yeah, good question. Okay, so now I'm going to process an image with this database. So here's my image. This is an island. This is an island. Here's you know, some sand. You saw that in my image the other day. So this is very shallow, like 2 meters right here, goes down to about 10 meters here. Here's Lee Stocking Island over here. All right, and so I've got this image. I go in, I pull out this pixel. So here it is. And then I do the atmospheric correction. Then I take the atmospherically corrected pixel and I search through the database and I find the closest matching database spectrum by some metric. It could be least squares, it could be absolute value difference. You know, we've looked at like a dozen different spectrum matching or a dozen different ways of saying one spectrum's close to the other, and something like least squares works just as good as anything. But anyway, some way or another, you search the database and you say, here's my closest matching spectrum, which in this case is the red curve. And you can see in that database of 250,000, there was a spectrum that was extremely close to the one I measured. Okay, so now I've got my closest matching database spectrum. I look in the database and I say, what were the IOPs, the bottom reflectance, and the bottom depth that go with the red spectrum? Well, in this case, the depth was 2.75 meters, the bottom was 80% sand and 20% grass, and it was IOP set number 17, which is plotted here. So there's absorption, there's absorption including water, scattering, and backscatter. So I say my retrieval for this pixel is 2 3/4 meters deep, sand with a little bit of seagrass, and here's the IOPs, and that's my retrieval. And now I go to the next pixel and repeat the process. Yeah, Jason?
But that doesn't get over the problem with the atmospheric correction.
Well, that's already been done.
But if you've got a bad atmospheric correction,
Right, yeah.
you're going to come up with a bad...
Right, right. And see, here's my actual spectrum. You notice this guy's going in at something non-zero, and then you atmospherically correct it. It's actually down here at 0 plus or minus a little bit. So yeah, this is assuming that the atmospheric correction has been done and that it's a good one. And likewise, that your sensor is radiometrically well calibrated. Okay, so here's just an example. Here's another area in the Bahamas, Lee-Stocking Island beaches. So they have a lot of what's called ooid sand out there. Ooid means egg-shaped, so it's these little kind of egg-shaped looking little sand grains. But it's a very pure white sand like you see above the water here. There's regions of all kinds of mixtures of sediments, corals, turf algae, seagrass around in here. There's a coral reef here called Horseshoe Reef. Then offshore here, it's dense seagrass on the bottom, and this goes out to about 15 meters depth out here. And there's a nice coral staghorn coral reef right here, which is where the shark almost got me while I was snorkeling, but that's another story. And this shark, I swear, it was at least 10 meters long. It was huge. And never has anybody snorkeled and swum so quietly getting back to shore, so I wouldn't get the shark excited. Anyway, there was a big field experiment here called COBOP, Coastal Benthic Optical Properties. And the purpose of COBOP was to learn how to do things like remote sensing of these shallow waters. So the Navy sent out a guy in a small boat, and they spent weeks, literally, going back and forth getting acoustic bathymetry. So every little black dot here, there's an acoustic ping. And you'll notice deep water offshore, as soon as the guy in the boat gets up close to the coral reef or the shallow water, they turn around and go back because they don't want to sink their boat on the coral reef. But anyway, we do have enough data here, although the shallower waters we don't have too much, but that's life. So we have acoustic data at the black dots, and then I do my retrieval using this database lookup business, and I come up with the retrievals that are shown by the colors over there. So, 0 to 2 meters, and then finally down to more than 12 meters here. So how good did my retrieval work? Well, if we compare the retrieved depths with the acoustic depths, and I plotted those 4 different ways, in this particular image, I had something like 12,000 points where I had a retrieval. And so just as a scatter plot here, I'm doing pretty good. On average, I'm off by about 3% or about 1/10 of a meter. But, so that's good. You can see there's striping here, and that's because my retrieve depths have to be one of the depths that I used in my database. So it was like every 25 centimeters down to 10 or whatever it was, and then it was every half a meter down to